Hi everyone, in this video we'll learn about chapter 13 intermediate first year physics thermodynamics. In this chapter, according to blueprint, we will be getting 8 marks question. So from this chapter we will cover the most repeated and important questions. So without any further, let's understand the important concepts in a simple and easy way. This is the first question. State second law of thermodynamics. How is heat engine is different from a refrigerator? So first we have to state the second law of thermodynamics, which consists of two statements. First is Kelvin-Planck statement. It is impossible to construct any machine to transport total heat energy into work. So the next statement is Clausius statement. Heat cannot flow from a cold body to hot body by itself, but heat can flow from a hot body to cold body by itself. Okay, so the third one, what is heat engine? A device which converts heat energy into work is called heat engine. So this is a block diagram of the heat engine. Okay, so this is the source T1 and this is engine. From the source Q1 amount of heat is taken to the engine, and also Q2 amount of heat is released into the sink, which is T2K. This is a cold reservoir and this is a hot reservoir. So this is a block diagram of heat engine, and the essential parts of the heat engine are source, working substance and sink. So what is source? It is a body at higher temperature, T1K heat. Q1 is taken from the source. This is a working substance. In steam engine, the working substance is steam. In diesel engine, the working substance is mixture of fuel and air. Next one, sink. It is a body at lower temperature. It absorbs heat. Q2 rejected by the working substance. Next one is efficiency. The ratio of work done by engine to the amount of heat absorbed Q1 is called efficiency. So efficiency is equals to work done by Q1 amount of heat absorbed is equals to Q1 minus Q2 by Q1 is equals to 1 minus Q2 by Q1, or efficiency is equals to 1 minus T2 by T1. Okay, the next one is refrigerator. The refrigerator is a heat engine working in the backward direction. This is a heat engine working in the backward direction. So this is a block diagram of the refrigerator. This is a source T1 and this is the engine, this is sink, this is a hot reservoir and this is a cold reservoir. This is the heat engine working in the backward direction. So the amount of heat is absorbed from the sink. Q2 amount of heat is absorbed from the sink, and then the work done is done in the engine, and Q1 amount of heat is released into the source. So in refrigerator, the working substance absorbs Q2 amount of heat from the sink. So in refrigerator, the working substance absorbs Q2 amount of heat from the sink, and external work done W is done on the working substance, and finally amount of heat Q1 is rejected to the source. Efficiency of the refrigerator is called coefficient of performance beta of the refrigerator. So beta is equals to Q2 amount of heat from the sink by work done is equals to Q2 by Q1 minus Q2 is equals to T2 by T1 minus T2. So this is the important and most repeated answer from the previous paper. So let's move on to the next question. So moving on to the next question, explain reversible and irreversible processes. Describe the working of Carnot engine. Obtain an expression for the efficiency. First we have to write the definitions for the reversible and irreversible process. Then we have to write the definition for the Carnot engine, then diagram, then the derivation part. Okay, so first one, what is reversible process? A process that can be retraced back in the opposite direction is called reversible process. Example, fusion of ice and vaporization of water. Next one, irreversible process. A process that cannot be retracted back in opposite direction is called irreversible process. Example, diffusion of gases. Now Moving on to the Carnot engine. A reversible heat engine operating between two different temperatures is called a Carnot engine. This is the diagram of the Carnot engine. So the y-axis is pressure and the x-axis is volume, and this is the point A, pressure 1, volume 1 and temperature is 1, and at point B, pressure 2, volume 2 and the temperature is 1. At point C, P3, V3 and T2. Here the temperature is same and here the temperatures are different. The heat engine operating between two different temperatures. Here the temperature is same and here the temperature is different. So we have two different temperatures, okay? Now here let's write the derivation. Working of a Carnot engine. Isothermal expansion W1 work done is equals to Q1 is equals to nRT1 log V2 by V1. Adiabatic expansion W2 is equals to nRT1 minus T2 by rho minus 1, and isothermal compression W3 is equals to Q2 is equals to minus nRT2 log V3 by V4. Adiabatic compression W4 is equals to minus nRT1 minus T2 by rho minus 1. So work done is equals to W1 plus W2 plus W3 plus W4. So these four equations we must write, okay? So after writing all the four equations, we have to write the remaining nRT1 log V2 minus V1 minus nRT2 log V3 by V4. And again T1 nR log V2 by V1 minus nRT2, this is T1 and this is T2 log V2 by V1. So work done is equals to nR log V2 by V1, and therefore here T1 and T2 is there, right? So T1 minus T2. So therefore efficiency is equals to work done by Q1, right? So is equals to nR log V2 by V1 T1 minus T2, this is the work done equation, by nR log V2 by V1 and T1, this is a Q1 equation, right? So therefore efficiency is equals to T1 minus T2 by T1. So this is a Carnot engine derivation.